Hi. So today I'm talking about web transport, a new protocol over the web that you might think of and in shorthand as WebSocket 2.0. By not calling it WebSocket, they're able to let go of the legacy and try to paint a new picture for the web in terms of bidirectional, unidirectional streaming, as well as datagrams and that sort of thing, which we'll talk about. We'll also look at WebSockets and SSE, which is the current state of streaming in Ruby. It's what we're doing today. It's what we've been doing for many years, but it is evolving. And so we'll look at how it's evolving. And then finally, we'll take a look at chunking, which is a venerable late 1900s style of streaming. But it's something that modern projects outside of Ruby are actually utilizing today in novel ways. So we'll take a look at that briefly as well. So web transport. This is a spec that is semi-supported at the moment. There are folk using it in earnest, and it's going to be probably getting a lot more popularity here soon after its drafts are released. So right now, the World Wide Web Consortium, the WC3, has a draft living standard for web transport. So browsers do support it, Firefox and Chrome currently, and Safari shortly. The Internet Engineering Task Force also has a well-developed HTTP3 spec for web transport and an upcoming HTTP2 spec. So this is something we'll see throughout the talk, is that there's a pairing of the browser side to get a web API with the IETF side to get a transport protocol. The transport protocols can be used without the browser. The web API gives you the hooks in the browser to be able to use it from Firefox, Chrome, Safari, the browsers we love, and all the others. So web transport, unlike the protocols we use today, is in a single transport, both unidirectional and bidirectional. So what does that look like over the wire? We have data represented here as 1, 2, 3, 4, 5, 6. It all goes from server to client unidirectionally, or the other way around, from client to server. Bidirectionality is the same thing as unidirectionality, but both ways at once. Full duplex, we used to call it. And then partial reliability even, where maybe some keyframes make it through, because in web transport, we have a concept of priority. And so in things like video, you can have frames that are essential for rendering the next frame, and then you can have filler frames that if they don't make it, the user may not notice, but it's going to provide additional information. And there's lots of times where we want to say, I want partial reliability. Some of my packets need to stream with retries until they make it, whereas others try once or twice, maybe try once and let them go because they're no longer going to be relevant. So web transport doesn't just support streams. WebSocket and SSE is streaming only. Web transport also supports datagram. It has less overhead. It is unreliable. It's not going to try again. If the packet is dropped by a proxy or just doesn't make it for unknown reasons, it's gone. And it's unordered. If one of the packets makes it before the other, it will be there first, and it's not going to ensure that one comes before two, but comes before three. But today's talk is about datagrams. So that's about all I'm sorry, about streams. So that's all I'm going to say about datagrams. So it's interesting that this web transport is actually HTTP3 with HTTP2 fallback, because it's starting actually with the later protocol, and we'll see later why that's a bit strange. It does have some real advantages, like end-to-end sessions to streams, which we don't have at all on today's protocols. So this means that we can have many sessions over a single web transport connection, of which a browser can have 8. We can have many streams, and they just thought, let's pick a number. 64,000 sounds good. Most browsers are saying, how about 100? So we have kind of like, if you're going between Ruby on both ends with the web transport, you can do quite a few streams. The streams will share lower layer transport frames. They will be able to share sessions, and the flow control and congestion control will be done at the web transport layer for HTTP2 and at the QUIC layer for HTTP3. So web transport soon, but not yet. This is exciting because it gives us some novel capabilities, some of which we haven't ever seen because they're novel. But it also allows us to use some of the protocols that we've gotten accustomed to firsthand, and we'll see how that works later. So, but first up, let's look at the present. So up to current, we've been talking about web transport, which is sort of forward-looking. If you do it right now, you're certainly cutting edge. WebSockets are battle hardened. Just like web transport, they have a WC3 living standard. The browsers, it's just whatever they're currently doing. That's the spec. And they also have an internet engineering task force RFCs, multiple RFCs, because we've had years and years of WebSockets at this point. This is pre-WebSocket at the end of the 1900s, which we mentioned. HTTP 1.1 brings about modernity, and with it, persistent connections. It takes 12 years for us to see WebSockets on the stream with RFC 9455. So these RFCs are actually pretty good reads. They're not that technical for being technical documents. I guess they are technical. There's technical as you can get, but they're readable. And what this brings to us in 2011 is the upgrade method, a new method for headers. So we look at a GET request. In HTTP 1.1, this is pretty typical. We say upgrade to what type? WebSocket. And this is a connection upgrade. It's basically saying we want to replace this TCP socket with another one of this type. Can you do that? The spec says, give me a 101 response. So 101 is I'm switching protocols. Like, yes, we'll do. To what? A WebSocket. And so this handshake, additional handshake, takes a full hijack of the TCP connection and basically says, start a new one. And instead of HTTPS, start it with WSS, start it with a WebSocket one. So we may have some issues with, we're now sort of going to a different place. The full hijack part is supported by Rack. Rack adds this shortly after these. So it can stream, it can basically make a regular connection to Rack. Rack has a way to say, yeah, we're not handling this. We're going to say this is getting hijacked. Just like we're switching protocols. So it lets us support WebSockets. We have HTTP2 come then in 2015, shortly thereafter. And a lot of folks said, why did we just get this new protocol? Because HTTP2 is also full duplex. It can go in both directions at the same time. So are WebSockets dead? And folk could immediately kind of begin communicating with HTTP2 back and forth between, like, say, a Ruby program and another Ruby program. But there's no web API. And 3 years later, we see no, WebSockets are not dead. They are going to be supported by RFC 8441, which bootstraps WebSockets on top of HTTP2. And actually, this brings with it not only compatibility, but some real advantages. There's a new header. We connect WebSocket, a single header, and that can go over an HTTP2 stream, which, because H2 supports multiplexing, you don't have to start a new connection. You can just say, start a WebSocket stream. We can do lots and lots of these. And that way, we have no new handshake, no reconnection over a separate socket. And we get some nice things like HPAC, or depending on your perspective, maybe not nice, because in HTTP 1.1, you could just look over the wire at the ASCII characters that would read get, etc. And now you look at a bunch of gibberish binary. But HPAC is significantly quicker, and the HTTP2 protocol, I'm not going to go into detail, but it's very interesting, is able to do handshakes faster and take on some lower latency, especially with connections. So Rack 3 streaming, also paired with HTTP2, gave us some interesting capabilities that we didn't have before. So let's first look at what is Rack 2 streaming before we look at Rack 3 streaming. So Rack 2, you could do chunks. You could support that HTTP 1.1 standard from 99, and you could do it by having an enumerable. So as long as it responds to each, and that means you can use an enumerator. You can put sleeps in there. You can pause, you can wait for the next part of a CSV to be available or whatever you want to do. But you're not going to be able to handle the stream. You're just giving the rack something that can be iterated over. I mean, it's going to take those chunks and pass them on But in Rack 3, we got a new, instead of responding to each, a new streaming style. And this gives us something that responds to call. You pass it one argument, which is the stream itself, and then you can write to that stream. You can read from that stream too. So it's bidirectional, very much unlike iterating over each. There's no way to get anything back. And importantly, you can close the stream, which both lets you say we're done, but it also lets you communicate information back to the browser. So in 2021, we then had HTTP3 QUIC, which QUIC, folk don't usually use it as an initialism. It's just, you just say QUIC, but it is UDP, fast UDP. And what that really means is in TCP, we have ordered, reliable connections. UDP is used for these datagrams that we talked about in web transport. And they're great for things like games where you just gotta, it's like, if it didn't get to you, it's too late. We're not retrying. Like the next packet is the one we care about now. They're unordered. If one's slow and you see the timestamp's out of date, you just throw it away. You don't care. But QUIC takes on top of this UDP protocol, a lower level protocol in many ways than TCP, and it adds in things like reliability and order as optional things, and it does it in a way that pays more heed to things like flow control and congestion, and also into flexibility. So why are we doing this? In large part, head of line blocking gets significantly better when you try to do congestion control on top of UDP as opposed to TCP. TCP, head of line blocking, is if something is ahead of you and it gets blocked, you don't go anywhere. So it's like if you're in a line at the grocery store and someone ahead of you gets stuck, there's no, like, they have other lanes that you can go into, but if they don't, then the whole line gets stuck. So HTTP3 lets WebSockets work just like HTTP2. Only 1 year later, they announced that we could bootstrap there because they just followed the HTTP2 spec. Like you're going to see that request and response will just look exactly like HTTP2, but you're going to get that same thing with less head of line blocking. So in Ruby, we'll be able to use WebSockets, and if the underlying protocol is H3, it's just less likely that one of your earlier packets or a packet from something else that you're streaming, like SSE, will block the whole world. It's kind of like stop the world garbage collection. It's not good. We want to avoid it. And each iteration of this, we're doing better. So it uses connect WebSocket, but it's a little different as a header over the wire because HPAC just compressed connect WebSocket down a bit. Whereas QPAC actually did some analysis. It's what they use in QUIC, sorry, the Q for QUIC. But they actually did some analysis of what are the popular things we're sending over the web. And it turns out Connect WebSocket is extremely popular. So you just get to send a single byte now, 15. 15 means that you got yourself a WebSocket. There's a lot less head of line blocking too. So what we've talked about to this point is basically WebSockets and WebSockets over HTTP2 and HTTP3, and then yikes, we don't want to be held back by the mistakes. Like looking at the IETF meeting notes, which are online on YouTube, you can just watch the standards folk talking about the standards they're building. But they said, someone said like WebSockets pointed the ship in the wrong direction, and the chair, I believe, of the committee said that ship has already sunk. And so they're sort of kind of actively trying to sink WebSockets. But at the same time, we can't use web transport yet, and we won't be able to for quite some time. So while the ship may have already sunk, according to the standards committee, we're going to be using it for years to come, and we should, because standards precede the real world. So SSE actually did not precede WebSockets. It was the same year. It's just, it was the World Wide Web Consortium acting unilaterally without the need for any internet engineering protocol fuss. So they focused on the web API. What they don't have is bidirectionality. It's a one-way stream from server only to client. You can't go from client back to server. And it looks very much like the TCP that it sits on top of, but it sends an HTML page that completes the end of end HTML element, and then events stream after it, ordered, reliable events. So let's look at a little demo. The front end code here is going to be HTMX. I'm just doing this so I don't have to write any JavaScript. But you could instead use some of the many other libraries that help us get here, like unpoly, et cetera, et cetera. So I'm also going to use a little extension for HTMX called SSE and WebSocket. They basically let you do the types of things that HTMX does, which is when we submit a form, it's going to be a post because the browsers thought we'd never need a get, put, and delete, right? But we do. We need to submit forms with those because we want different network and server-side behavior. And HTMX just sort of adds those via polyfill. There's actually a proposal, Triptych, which is just a couple hundred lines of JavaScript to extend HTML to be able to do these. But the extensions here truly are extensions that won't ever be, probably accepted into HTML that provide some things on top of SSE and WebSockets. And here we're going to see it look like pull in the script, and then the only content of this page, this is literally the whole content of the demo I'm going to show you, is 2 divs. I put a moon class on it just for some styling, and then use the extension. The extensions work similarly, except the WebSocket one, you specify like the behavior type, whereas the SSE one, there's different types of events. So they're slightly different in the same way that they are via the JavaScript API. On the back end, I'll use Roda, which Jeremy Evans created. Fantastic library. It's a rack Ruby web server if you haven't used it. And Roda plugins are excellent. You take Roda, which is very little on top of Rack itself, but it adds in a routing tree. And then you can use the plugins that Jeremy Evans created, as well as you can create your own plugins. And so in order to make your Roda routing really elegant and to provide the things that you need to reuse, a reusability way to actually reuse your code, plugins are fantastic. So I created 2. One is under my GitHub, github.com/havenwood/Roda SSE. And the other one is under the async GitHub repo socketry, and it's socketry/Roda-WebSockets. These both use the excellent async fiber libraries because when we're going to be streaming, we want to be doing it with a whole bunch of clients without taking a thread per, as many of the other Ruby solutions do today outside of async. So let's look at our Roda code. This is the plugin for render, which ships with Roda. Lets us show an HTML page easily by convention and use tilt, as well as the ones I wrote for SSE and WebSockets. And we're going to animate an emoji moon spinning. On the SSE route, this is the plugin. We say if it's SSE, meaning it's a GET request and et cetera, then we're going to put the SSE headers on it and use the Rack 3 streaming interface under the hood here to actually write the payload. So for SSE, we'll talk about this more, but we say data : because this is the World Web, the WC3 that wrote this spec. So they just said, let's just put data in front of the data and like ID in front of the ID and put it in a simple string, and then we'll just use new lines to say we're done. And then in the WebSocket, it's very similar. We just flush to say we're done, flush the socket. So if we look at how these look, they're pretty similar. They're not going to get too out of sync because if one blocks, it's going to actually end up blocking the other. If we kill the process and let it hang up, they don't stop exactly at the same time. The SSE one will restart on its own due to the spec. But you could emulate that same behavior in WebSockets, and folks typically do. So the web API for SSE is what makes it different. It's what distinguishes it. And in many ways, it's also what we can just replicate at the JavaScript layer, but you have to write JavaScript. So event type callbacks, you can do this if you want to send JSON over WebSockets and then figure out what you sent, and you come up with your own protocol for it. Last event ID header is in the case of failure, the browser will automatically send back the, if you send it an ID, which is optional. People think that SSE is self-healing or something. It really isn't. You have to care. You have to send it an ID, and then the browser, when it retries, will automatically in the spec, really the real spec from the WC3 says retry in a few seconds. Which browsers have interpreted as, of course, the spec 3 or 5. And they didn't specify jitter or exponential fallback, which I think in retrospect we wish they had. But we typically provide those, like HTMX plugins provide that both for SSE and for WebSockets. They provide jitter, so the initial, like let's say your whole server goes down. You come back up. You don't want 3 or 5 seconds later, depending on your browser, the whole stampede to hit you at once. And so putting in some jitter, so each person is like, I'm going to connect at 2.5 seconds. I'm going to connect at 5.5 seconds. And then they can each exponentially fall back. So you're not going to have these stampeding herds. So these are some simple abstractions when we actually use them. They're complicated under the hood, but you can use them on the browser and use them on the server with only a couple lines. So they also look very much like each other. So we can use a proc to represent both of these streams. There's a slightly different body, so I had to say SSE stream to get that data thing in there. But when you look at them in Roda, the plugins make them, you serve the SSE stream, serve the WebSocket stream. You want to serve web transport? Well, we can save some overhead by saying it's unidirectional, but it essentially looks the same. And I think the important thing here is for unidirectional streaming, we can write a plugin that tries to connect over web transport. And if it doesn't have an H2 or H3 client, falls back to WebSocket, which will connect over 1.1. And then 2% of WebSocket connections typically just fail. They say, please switch protocols. And the server dutifully says, yes, switching protocols. And then no traffic ever comes over that new socket. We don't exactly know why, but probably proxies. And this is probably going to be an ongoing problem. And it's only going to get way worse for web transport, because even when people are using Nginx to reverse proxy HTTP2, typically like Rubyists often do, web transport needs real HTTP2. It can't just proxy over to HTTP 1.1 because no servers can handle that content negotiation. It's actually incredibly complex to do on top of HTTP2, and preferably should just be done on top of QUIC. So let's look at SSE from the CLI though, because while SSE is a web browser spec with no protocol for how you send it over the wire, you can use it from the client. Most people don't use it directly from Ruby or any other language. They use the browser. But if you wanted to implement SSE just to see what the browser is doing, you can, like here we have a Roda app that the plugin I wrote, you can take last event ID, it just pulls the header off, and then we're going to stream. And then you see that raise line on line 20. We're actually every 7 requests going to simulate an error to allow SSE to do its self-healing. So our front end, people just really don't use SSE as a browser protocol. So it's no shame on Ruby that no one wrote an event stream parser. So I just wrote one for this. And a little SSE Ruby client to pretend like I'm a browser, sort of do the same browser behavior of retrying. I put some jitter in because I just couldn't pick 3 seconds flat. So here's some code. Let's look at what this looks like. So in this same Roda app works with a browser. So here we're streaming some emoji. If it reset to the beginning, it'd go back to 0 pineapples. But as you can see, it carries on from where it left off. And this is basically the Ruby is acting as the browser. You could have a browser connect to the same backend at the same time, and that would work. So I don't recommend using SSE as a protocol, but it is interesting to look at. It's a fun exercise and fairly easy exercise to implement the browser behavior for. So SSE also supports types beyond message. So messages, if you don't give SSE a type, it says, we'll call that message. And that's in the spec. So let's look at types. So here we have another Roda app. I'm going to specify a message is basically being pushed onto the stream. So what's the message? Here, the message is going to be some HTML. So we have a div. The class is going to be a grid item. And we're going to SSE swap. So we're going to use the HTMX SSE extension to just swap the div with the pixel number of the pixel that we're wanting to swap with a random color. And then I just have a couple of Ruby methods down there below to pick a random pixel to give it a random color. So the front end here is including the extensions, and then we serve up the initial screen, which is just going to be a grid item of all black squares. So this grid item, we're just using divs. This is a screen of divs. There's no content in this except for divs. And we've got 2 divs wide, 2 divs high, 4 divs per second. We're just gonna push over the wire with Roda. So there's a couple extra headings in here for quicker Roda connections. But here you see those 4 divs changing color via that one SSE connection. So what if we want to up it to 20 by 20 and do 40 per second? So let's restart Falcon. It can handle this, no problem. You can do quite a few of these. If you want to go to havenwood.dev, I have it running right now. I won't leave it running. But and this is just a lot of divs on the screen. If one of these gets blocked, it's going to block all the other updates. And if you have a bad internet connection, like in a hotel conference room, that's more likely. So yeah, you can see how but it remarkably works most of the time. As you bump it up, this is 40,000 divs. Updating at, and we'll refresh, we restarted Falcon. And you see here, we're starting to see it. If you want to go to havenwood.dev and look at your web inspector, you're going to see a flurry of events as thousands a second are trying to go across the network. But this is not really appropriate for sending video over the web. But what if we tried? Let's go ahead and use FFmpeg to turn video into PNGs, and then let's down-res it, and then let's use ImageMagick to compare every frame. And let's do a diff to see which, if any, pixels change. And if a pixel doesn't change, do nothing. But if a pixel does change, fire off an event for that pixel to send a div with its background color over the web to the browser. So for the sake of the demo, I did not pre-fill the actual image. I started with just a black screen, but this is only my diff passing thousands of divs, the update for its background color using SSE over the web. No modern protocols. And it works. So what does web transport actually open up for us? Web codecs. So this is coming down the spec pipeline right now. It's not finalized, but right now, if you want to send video over the web, it's WebRTC. And WebRTC NX is also coming down the pipeline, which can work on top of QUIC and can even maybe web transport. But what web codecs let us do is say, you know, yeah, we're not going to be sending divs across the wire for like video. Smart people have worked on this, and they've come up with a better way than I have. And those codecs can be easily integrated into web transport. Web transport can pay attention to the priority of the codec and can send the bits across the wire in the appropriate way, whether it's partially reliable, whether it's datagrams. And this is not something we can do with SSE or WebSockets today, which is why we don't do it. But this is going to open up new things beyond video. So I think part of this talk is to say, I don't know what we're going to do with this, but it's going to open horizons and we're probably going to want it. So SSE issues, obviously unidirectional, that's huge. Head of line blocking suffers from the same thing as WebSockets, but it does just work. It's not 2% or 30% of requests that fail. It tends to just work. So you see SSE 2012, 2015, 2021, it just got these new protocols. It didn't do anything. Because it doesn't have a transport protocol. It uses the underlying transport. WebSockets got the initial version the same year as SSE. And then it took a while to get the H2, and the H3 version came right along. Web transport going in a different way. It will never support HTTP 1.1. It is adding things on top of the TCP protocol that are frankly incredibly difficult to do on H2. So H2 spec is not in browsers today. You cannot connect to web transport over HTTP2. That is scheduled for mid next year, and won't even be in Chrome and Firefox until maybe around this time next year. So we're going to see HTTP3 come first for web transport, which is a first. It may actually come in the coming weeks. It is near completion and has been implemented by the major browsers. We're going to see the HTTP2 version maybe finalize around sometime in 2025, maybe early 2026. So this is a real challenge because this means that we're going to have to, one, implement HTTP3 in Ruby or be able to get it from somewhere. But then two, we're going to need real HTTP2 web servers in Ruby. We can't just reverse proxy like we've been doing for ages to get at web transport. So let's take a look at Ruby's future. We have async HTTP, a great HTTP2 client. So if you want to send from the Ruby side to a server, we have good clients. HTTPX, pardon my inversion there, and NetHTTP2 use Ilya Grigoric from Google's seminal work in Ruby, natively implementing HTTP2 in Ruby. Very cool project. And then Typhoeus actually uses the curl, libcurl under the hood to be able to do HTTP2, even if we don't have a Ruby implementation. HTTP2 clients do have some differences between them. So you may, this is a spreadsheet I've done that includes a lot more, but these are some of the HTTP2 ones and the standard library ones. So we might need some more. HTTP clients, no, we don't have those, but there are some in the works, and I think it's important work, and we need some diversity in the ecosystem. HTTP servers, not Puma, Falcon, so we have one. There may be more. I'd love to hear about them. If you are creating one or see one, please let me know. Havenwood on GitHub and IRC and Discord and things. HTTP3 servers, no. Also coming, but no. So let's quickly digress into the world of JavaScript. Chunking is both, like, it came out in 1999 with HTTP 1.1, but people are still like using it today in novel ways. So we've looked at WebSockets and this WebSocket 2.0 web transport. We've looked at SSE. These are the things we use in Ruby. But you can do these without a web API. And that just looks like just keep sending more. But when you do HTML, you can't pick where it goes. It'll always be at the bottom of the page, unless maybe you do some fancy CSS. But you're just chasing with script tags. But people do this for real. Next.js with React Suspense actually just released a new version, and they are not doing exactly, this is a pseudocode, but they're basically doing the tactic of stream your, like, do a chunk that renders the HTML page, but don't close the body or the HTML tag. Just sort of leave it hanging with an open connection. And then you can push the next chunk with a div that's hidden, and I just put it at display none, but they're hiding it off the screen of the browser. And then you basically juggle with the virtual DOM and unhide it over the div that it's replacing. This gives you incredible flexibility to push your JavaScript over the wire after your payload, because you can do anything you'd like from the server. But it also means you are writing JavaScript for the browser on the server. So we probably, with Ruby, want to do this in a different way. So our hope is in Amsterdam in April, there are beautiful flowers. No, that's not it. It's QUIC in the kernel. QUIC is incredibly difficult to implement. And unlike things like UDP and TCP, they don't say, Ruby, would you please implement these? They say, please use them from C or from your implementation, whatever language it's in. Use the kernel implementation of these things. QUIC is not in the kernel. And iAquatics assisted me with the, who does the async and assisted me with the Roda SSE plugin, and mentioned, he would like to see, as I would, QUIC in the kernel to save all of these languages the hassle of implementing them. Some already have, looking at you, Rust, Go, Python, Elixir, Erlang. But we are not necessarily terribly close, but at least we do have work in progress to get QUIC for Ruby. And this is going to be something that we may not have urgent need for it yet, but these protocols are in progress and are going to become real, are going to become used, and we're going to want to have them, especially the truly mainstream ones like WebSockets 2.0. So iAquatics, you can sponsor online, but this is one person who's doing great work. We need more people working on these protocols. We need more people supporting iAquatics's work with documentation assistance, with bug fixes, and with enterprise support to add features that most of us don't use. But iAquatics worked on things like Falcon, our one HTTP 2 web server, like async, one of our 4 HTTP 2 clients, all the async libraries that support them, the underlying protocols that are super important to make it work, and then things that actually land in Ruby, like the async fiber schedule, the scheduler that landed in Ruby 3.0, like native fiber coroutines. So we have coroutines that are native on top of our architecture and operating system, and things like IO event and IO wait and IO buffer. So we have ways to work with our buffer, and we have ways to get at epoll and KQ for evented IO from Ruby itself at the library level, and not just for these things, but any of us can use this to make new solutions. So I'd love to see sponsorship for Protocol QUIC, Protocol QPAC, and Protocol Web Transport in particular. Protocol QUIC is the biggest one because you may not believe that Protocol Web Transport is going to take off, but Protocol QUIC is already 30% of the internet traffic. According to Cloudflare, it's 3 times the HTTP 1.1 traffic. Most traffic is H2, but a lot of that isn't true H2. It's reverse proxied to a 1.1 web server on the back end. So I also want to say I love Roda and its plugins. Thank you to Jeremy Evans for making it. And there are a lot of other beautiful libraries in Ruby to build your own web framework, to compose it the way you'd like. I like the way you can do it with plugins. Other frameworks like Hanami compose it internally in a different way, but really great to work with and a joy in Ruby. So this was streaming over the web. I have a lot more to say on this, but only 30 minutes and I've gone over. But I'd love to take any questions since we're up against lunch. But if anyone would like to leave, please feel free. Lunch is beginning in 10 minutes.